In this video, we're going to talk about enzyme kinetics. In the last video, we talked about how enzymes are proteins that increase the rate of a reaction by decreasing the activation energy. In this video, we'll focus on how fast enzymes are able to convert reactants into products, which is known as enzyme kinetics. And it's important to understand this because many drugs exert their effects by decreasing the rate at which an enzymatic reaction is able to occur. We often think about reactions as being when one or more substrates turns into a different product. But it's important to be aware that for enzymatic reactions, there's an in-between step where the substrate must form an enzyme-substrate complex, and only then can the substrate form into the product. The formation of the enzyme-substrate complex is a reversible reaction. So this enzyme and this substrate can come together in the forward reaction, but the enzyme-substrate complex can also come apart into the enzyme and substrate in the reverse reaction. We'll refer to the rate at which the enzyme and substrate come together to form the construct as K1, and this is the rate constant. And then we'll refer to the rate at which the substrate-enzyme complex comes apart into the enzyme and substrate in the reverse reaction as K-1. This first step of the reaction, where the substrate and the enzyme bind to one another, is known as the binding step. The second part of this reaction is the enzyme-substrate complex forming the product and the enzyme breaking off from the product, and this is known as the catalysis step. This step is going to have its own rate constant, known as K2, and then this is also technically a reversible reaction, so that's going to have a reverse rate constant of K-2. But we want to be able to study the kinetics of this entire reaction, and not just the binding step and catalysis step separately. And that's where the Michaelis-Menten equation comes in. I'm going to go through the derivation of the Michaelis-Menten equation because I find this information as helpful background, but it's not strictly necessary for answering most step 1 questions about enzyme kinetics, so if you'd like, you can skip forward to the section titled Michaelis-Menten equation interpretation. In deriving the Michaelis-Menten equation, we need to make a few assumptions. The first thing we assume is that enzyme binding occurs much faster than enzyme catalysis, so catalysis is going to be the rate-limiting step. Since the binding step occurs so quickly, it will rapidly reach equilibrium such that the formation of the enzyme-substrate complex occurs at the same rate as the breakdown of the enzyme-substrate complex. This means the overall concentration of the enzyme-substrate complex remains constant throughout the reaction. We're also going to assume that at the very beginning of the reaction, no product has formed yet. And we're going to assume that at the very beginning of this reaction, the concentration of the substrate is a lot higher than the concentration of the enzyme, which means that the substrate concentration will basically be constant at early time points because the amount used up at this point is negligible compared to how much remains. The overall reaction rate is going to be determined by the rate-limiting step, which we said in assumption 1 is going to be this catalysis step. That means that our initial velocity, which I will refer to as V0, is going to be equal to the forward rate of the substrate enzyme to the enzyme and product reaction minus the reverse rate of that reaction. So the forward rate is going to be the forward constant multiplied by the enzyme substrate complex concentration minus the rate of the reverse reaction, which will be the reverse reaction rate constant, times the concentration of the enzyme and the concentration of the product. But remember that we stated in assumption 3 that at the very beginning of the reaction, which is when we are measuring the initial velocity, the concentration of the product is 0. So this last term can actually be eliminated, and we wind up with just V0 is equal to K2 times the enzyme substrate complex concentration. So this is a pretty straightforward equation, but we run into a practical problem, which is that measuring the concentration of the enzyme substrate complex is not straightforward. We can measure the concentration of the substrate, and we can also measure the concentration of the total enzyme, but we don't have an easy way to differentiate between enzyme that is bound to substrate and enzyme that is not bound to substrate. So we need to rearrange the enzyme substrate complex in terms of things we can actually measure. We can do this using assumption number 2, which states that the enzyme substrate complex concentration is constant because its formation and its breakdown is equal. So let's take a look at the things that are contributing to enzyme substrate formation. That's going to be the forward reaction of the enzyme and substrate forming the enzyme substrate complex, which is going to be the rate constant K1 multiplied by the concentration of the enzyme and the concentration of the substrate. And then theoretically, the reverse reaction of the enzyme and the product would also contribute to the formation of the complex, but since the concentration of the product is 0, as we stated in assumption 3, that's not going to contribute to the rate of enzyme-substrate complex formation. And then the things that are going to contribute to the enzyme-substrate breakdown is going to be the forward reaction of the complex to the enzyme and the product, as well as the reverse reaction of the complex to the enzyme and the substrate. Since the concentration of the enzyme-substrate complex is in both of these terms, I can pull it out, and then I can solve for the ratio of the enzyme and substrate concentrations and the enzyme-substrate complex concentration, which looks like this. And this term is known as the Michaelis-Menten constant, or the Km. And we can rearrange this equation to look like this. And then remember that I mentioned earlier that we can't easily measure either the enzyme that is bound to the substrate or the free enzyme, but what we can measure is the total amount of enzyme. And we know that the total amount of enzyme is going to equal the enzyme-substrate complex plus the free enzyme. And if I rearrange this equation to be solving for the free enzyme concentration, that's going to get me that the free enzyme concentration is equal to the total enzyme concentration minus the enzyme-substrate complex. And now I can substitute this term in for the enzyme concentration here. That'll get me that Km times the enzyme-substrate complex concentration is equal to the total enzyme concentration minus the enzyme-substrate concentration, all of this multiplied by the substrate concentration. And I'm not going to show all of the steps here, but if I solve for the enzyme-substrate complex term, so that's going to be the one right here and here, what I wind up with is that the enzyme-substrate complex is equal to the concentration of the total enzyme multiplied by the concentration of the substrate, and all of this can be divided by the Michaelis-Menten constant plus the concentration of the substrate. So now I can go all the way back to my initial equation that V0 is equal to K2 times the concentration of the enzyme-substrate complex, and I can sub in this for the enzyme-substrate complex up here. And that will get me that V0 is equal to K2 times the concentration of all of the enzyme times the substrate concentration divided by the Michaelis-Menten constant plus the substrate concentration. Okay, so at this point we're going to define one more term, and that term is going to be Vmax. Vmax is the maximal velocity that the enzymatic reaction can occur at. This is going to occur when the substrate concentration is very, very high, because it means that all of the enzyme present is going to have a substrate bound and will be working at its maximal capacity. So let's think about what this equation will look like when solving for Vmax, so the maximal initial velocity of the enzymatic reaction. This is going to occur when the substrate concentration is very high. And if this substrate concentration is very high, the Km in the denominator basically becomes negligible. So we can kind of cross this out. And then once we've crossed that out, we can cross out the substrate concentration in the numerator and in the denominator, and we wind up finding that Vmax is equal to K2 times the total enzyme concentration. So now we'll sub in Vmax for this term right here, and what we end up getting is that V0 is equal to the Vmax times the enzyme substrate concentration divided by the Michaelis-Menten constant plus the substrate concentration. And this here is going to be our final Michaelis-Menten equation relating the concentration of the substrate to the initial velocity of the enzymatic reaction.